Okay, yeah, so yeah, today we'll continue to discuss the classical mass equation, describing basically the geometry of beam model on Calabi-Yau at the chain level. Oh, by the way, besides the paper with Castello that I mentioned, I'm following the other references for this formalism. One of them is this one, which I wrote a review on this construction, classical quantum aspect of Calabi-Yau moduli. You can find it on my website, and another one which I'm going to use in the next talk and tomorrow. Renormalization method and the mirror symmetry. Okay, so to illustrate the basic idea, like how the stuff we have been discussing is related to topological gravity. So let me start with some point model. Let me describe a little bit about the geometric aspect of this gravitational descendants in pure gravity. So to illustrate the feature, so we consider the first case. Like say, my Calabi-Yau is just a point. Simplest Calabi-Yau, so cannot be simpler. Zero-dimensional space, point. Now, under this space, like our space X and so on, it's going to be like S is going to be Laurent series in this T, and S plus is the non-negative orders, and S minus is the negative powers. And so let me first explain this situation. And at the end of the day, we'll see like the general case for Calabi-Yau, it's going to be the shift version of this guy, this kind of object. So that's the essence. Actually, that's the essence of the BSI, which is localized to constant map. Okay, so now this sympathic pairing is given by the following. So there's no trace map now, but you still have the residue pairing, which is again sesquilinear. So T-linear in F and sesquilinear in T. And that's the setup. Okay, again we have the pairing map. So still let me draw the picture. So now this is my S plus, and then we have a pairing map. Again, let me call this P to now this space. Okay, this time I'm gonna draw this like that. So Kona will be much happier. Yeah. Yeah, this map is like FT. Map to here is like T e to the minus f of T. Again, this is a map that's in the category of formal scheme. Okay. Now, the same argument, I mean, it's actually simpler. So the image of the pairing map is a formal Lagrangian subspace. Lagrangian manifold. And now, under the choice of this splitting, using this symplectic pairing, we can write this space S as the cotangent of S plus, the same as before. So this is my S plus. This is the cotangent fiber, which is identified as the S minus. Then the same thing, like, because this one actually is a Lagrangian submanifold, you can write this one as the graph of something. So here, this I naught is a function on the base. So it's a function on S plus. And now if we parameterize the space, let's say for every element here, let's say tau lies in this S plus by, for example, like I'll write this one as like tau equals tau 0. Let me write in the same way. Summation from k from 0 to infinity, tau k t to k. So here is the variable parameters of this S plus. Then we're going to write this action function I naught as a function of this tau k's. Our goal is to compute this guy. And along this line, you will discover actually a secret link between this Lagrangian geometry with the topological gravity. And basically, to proceed, we can write this Lagrangian submanifold to be something like, I'm going to parameterize this one by, so on this slice is parameterized by this point tau k, and this one is given by this fiber, which is given by the derivative of this function. So this image, this Lagrangian submanifold can be parameterized by something like that. Okay, from 0 to infinity, tau k tk. So this part is on this line, and because this is the image of the d something, the other one comes from, like, say, k from 0 to infinity, partial tau k, I naught, and minus t to the minus k plus 1. And this comes from the symplectic pairing. This sign comes from this discrete pairing as well. And let's denote this one by the whole function as a phi tau k. And let's try to figure out the geometry of this guy. Okay, so now this is a combinatorial problem actually. If you think about it, actually this is a purely combinatorial problem. If you do Taylor-Six expression, write this one as the d of something, you quickly get into trouble. I mean, in the beginning I tried a long time to calculate this one from this combinatorics. We end up with guessing the answer and find the result. And now we understand this is actually, there's a very geometric way to capture this result. So let me try to explain this. This first one, so the first one is called string equation. By the way, all these equations we're going to consider come from basically known stuff in this string theory. And we are following actually a beautiful paper by Giventel to describe this geometry in terms of Lagrangian cone. The idea is the following. let's consider the following linear operator. Let's call this one t hat. This is the operation acting on the space S. What is the operator? This operator has a naive meaning, like just multiply by t, like t to the k mapped to t to the k plus 1. So the very naive way of describing this operator, just multiply by t. Now we think about this one as a linear operator on the full space S. Let's denote L inverse to be the following operation. So this is actually on this space S. This is an invertible operation. So let me call this L inverse to be the inverse. So this operation is basically like multiplied by t to the minus 1, and will this linear operator. So whenever you have a linear operator on a linear space, we can view this linear operator as a vector field on the space. And this vector field is very special. This vector field is actually Hamiltonian. It preserves the symplectic structure. So this guy, which is symplectic, for example, you can just check by hand. If you apply this operation to something f and pair with g, it's going to be minus f L inverse applied to g. And the minus sign comes from the fact that this is a sesquilinear parent. Where is my parent? Yes. So this is really actually a symplectic vector field. Now we can write down the corresponding Hamiltonian function of this vector field. So for example, I just erased. Our symplectic form can be written in terms of coordinate. So this can be written as like k, like d tau k, d tau minus k minus 1. This is my symplectic form, which describes the parent I just erased. And the sign captures the sesquilinear sign as well. And you can write this one as, for example, if you like, you can write in a more symmetric way, like I plus j equals minus 1 to the j, d tau I, watch d tau j. So that's more intrinsic way of writing this this symplectic form. Then let's calculate the corresponding Hamiltonian function. So, and this L inverse, because it's basically multiplied by t to the minus 1, is the same thing as tau minus I plus 1 d tau I. That's what this vector field is. Then let's contract this vector field with the symplectic form to obtain its Hamiltonian function. And this is a very simple calculation. I'm going to do this for once, and the later calculation I will just tell you the answer. But first time, let's do it slowly. And if you contract this one with this guy, because symmetric, you basically can contract the first one and you kill the 1/2, and you get something like I plus j equals minus 1 tau I plus 1 and d tau j. That's basically, you contract this one with d tau I, you get tau I plus 1, and the next is the same. And it's antisymmetric, and you can kill this 1/2. And you can write this one as the d of something. I plus j equals 0 minus 1 to the j, tau I, tau j. This is the corresponding Hamiltonian function of this vector field. And we got the Hamiltonian function to be let's call this one h minus 1 equals, no, let's just little h to be, so let's say when I and j both equal to 0, this one term, and the other term like symmetric, then I think you got something like 1/2 tau naught square plus k bigger than 1 minus 1 to the k, tau k, tau minus k. That's what you get after this calculation. That's the Hamiltonian function for this vector field. I'm gonna keep this picture. I'm gonna write my parameterization here. Okay.
So you're looking at the diffeomorphism of S1 acting on M2 function of S1.
Diffeomorphism for
S1.
S1.
Well, this is a generator of the solid.
Yes.
One of the
yeah.
And then you look at its representation.
Exactly.
Which is like a function on S1.
That's right. Actually, you have the full Virasoro from L minus 1, L0 essential. Yes, yes.
So the whole is that representation viewed as a spinor representation of the diffeomorphism of S1?
Which representation?
Is S like a spinor
for the S1 action?
Why is this representation?
You only have the. It turns out the only symmetry you obtained is starting from minus 1. There's no minus 2 essential. They break the symmetry. So only 1/2. So probably that's not. Yeah. But it's actually, there might be some mysterious negative part acting on this open string part, but I haven't figured this out yet, so we can discuss. Yeah, that's actually a key point. But let me just tell you what's happening here. So here's the lemma, and this is one of the key aspects of given-tail formalism. And so this vector field is tangent to a shift of this Lagrangian by a dilaton. So this is my Lagrangian, and then shift by t. So this object is called a dilaton shift. And this appears a lot everywhere, basically, in this business. So let's take a look at why. Again, we're going to prove this first case, and then all the other cases like follow in a similar way. So let's take a point on the dilaton shifted point. So let's take, say, alpha to be an element here. So it can be written as like period map applied to some f and shift by t. So one of the point here. And in formula, it looks like because this is, this is like a dilaton shift basically kill this term. Minus t. But that's one of the points on this shifted Lagrangian. Not this shifted Lagrangian in that shifted degree. It's a dilaton shifted Lagrangian manifold. Too many shifted, yeah. So if you calculate the tangent vector, tangent plane of this dilaton shifted Lagrangian at the point f, say, if you really calculate this this guy. And say if you of this shifted Lagrangian, and basically the tangent plane come from variation for this f. So if you do variation for this f, what you find is like it's given by all vectors of the following type. Because you do variation for f, that's what you find, and the t cancelled out, and that's something like that. And then this tangent plane looks like, so you remember like f stuff capture all these non-negative orders. So this tangent plane is basically the original s plus, and with this vector, this weight, e to the f over t. That's the tangent plane at this point. And you look at this vector field evaluated at literally at the point f. And by the way you identify vector fields with a linear operator, the value of this vector field at f equals the vector of this L inverse applied to f. And then you see like when you apply, so L inverse behave like multiply this by t to the minus 1, and you kill this term. This equals minus e to the f over t. And you see like this order is non-negative and sits inside this tangent plane. So that's the proof. So for any kind of vector field, it's a linear vector. The way you write this vector field is like, okay, so if you really want to write this one as a vector field, phi is an element of redual tensor V. So this looks like a linear function, coefficient, and this is your vector field. And then the value of this vector field at the point alpha is basically evaluate this guy with the point. This is the function, right? You evaluate it as a linear function at this point and look at the corresponding vector. That's the same thing as evaluate this with alpha is the same thing as multiply. You apply this operation to alpha. It's a linear.
It just become multiplied by t.
Yeah. And then multiply by t inverse is like yeah. Okay, so now here's the metric. Once you have so this is like standard classical mechanics. So once you have a Lagrangian submanifold, and you have a Hamiltonian vector field, which is tangent to the Lagrangian submanifold, then you can write down a Hamilton-Jacobi equation. So by Hamilton-Jacobi equation, this one says like the corresponding Hamiltonian must be constant on the Lagrangian. So let's say if you restrict this Hamiltonian function to this Lagrangian submanifold, it must be constant. Yeah, this is a general statement. Whenever you have a Hamiltonian vector field tangent to the Lagrangian, then this holds. This is Lagrangian submanifold. This is a Hamiltonian vector field associated to some function. Tangent then implies that this one restricted here is constant. This is the Hamilton-Jacobi equation. And now we just plug in this formula. And by the way, it's easy to check. This is in this example, this is going to be 0 in this case. Just check a simple point. And then you just plug in. You restrict the Hamiltonian function to here. and just see what you find. And you see like tau minus stuff is valued by this derivative. So what you find is the following: like the first term 1/2 tau naught square plus the second term. I'm gonna write it as like a tau k plus 1, and the other negative part becomes this is like a tau. Originally you have tau k, something like that, with some minus signs, and this becomes derivative of this one. So with the sign correct, the minus sign corrected as well, so becomes a dv tau k and not. And then because of the dilatation shift, you shift the tau 1 by basically the value of tau 1, this is t to order 1 by 1. And you find the tau 1 value is just given by k equals 0. So shift by 1, you have the effect by dd tau naught and not equals 0. That's how you restrict this Hamiltonian function to this Lagrangian, and you just read off the equation. And the same thing as saying that dd tau naught and not equals 1/2 tau naught square plus some tau k plus 1 dd tau k and then you know a little bit about this commutative theory. This is known as a string equation for pure gravity. So the first thing we derive is like, well, no matter what this function is I know we want to compute it. It's a precise function. It satisfies the first equation, like string equation. This is one of the geometry of this Lagrangian submanifolds. Okay. Then the upshot is the following: like, we have enough symmetry to determine the whole generating function. That's the idea. So we have a lot of symmetry you can explore, and at the end of the day, just by exploring symmetry, you can compute this combinatorial object. So let me just tell you roughly how this goes, and be a little bit rough here. The next one is about dilaton equation. And this is about L naught. Now consider the operator. It's L naught. Applied to my S, it sends t to the k to this t plus 1/2 t to the k. The reason you want this k plus 1/2 is because you want this one to be symplectic. You want this one to preserve compatible with the symplectic structure. So in particular, you can show like L naught applied to F, G equals minus the same story. And basically, you pick up the sum of the degree, or t is to be the -1. So with this choice, this is true. Yeah. It's basically when ij has to, the sum of is -1, then the shifted 1/2 kills the 1 -1, and then the sum of these two is 0. So let me write in such a way.
Does it correspond to the S-mode diffeomorphism of S1?
This rescaling. So this is this operation. So yeah, that is one. So but this but it shifted a little bit. So
because you did central extension, or what?
Because I want it to be Hamiltonian. Yeah. This is a Different models, this will be defined in different way as well. So it depends on the degree of this symplectic form. But in this here, like for this model, the L naught goes like that. And for club of different dimensions, and this is related to the Hodge gradient. You remember the Hodge gradient? Yeah. We will see an example later. But in the point case, there's no Hodge stuff, and then that's the simplest case. Okay, then you can write down the corresponding Hamiltonian functions and things like that. So this Hamiltonian function and it's very simple to calculate. The same story. You will find to be k plus 1/2 tau k 3 tau k. And this vector, oh sorry, what is that? Minus 1 to the k minus 1 and minus, yeah, that's remember the derivative. H0, yes. Yes. This Hamiltonian function generates this linear transformation. Because it's linear, so every Hamiltonian is quadratic, basically. So far, by the way, all the Hamiltonians are standard Hamiltonian, even Hamiltonian. Later, we explore the odd Hamiltonian. So if you play with odd Hamiltonian, then you will discover like classical mass equations, things like that. I erased, yeah. So now the same thing, like you can show lemma, like this L naught is tangent to the dilaton shift. And the proof is similar, so I will leave this for an exercise. And then we have the same story. We're going to write down the corresponding Hamilton-Jacobi equation. So again, by Hamilton-Jacobi, we're going to restrict this function, this Hamiltonian function, to this Lagrangian, and you will discover. So let me just write it down. So this is like k equals 0 from 0 to infinity, k plus 1/2 tau k restrict to this shifted Lagrangian manifold is 0, and then you read off the data and also remember the dilaton shift, and so you will discover, for example, the dilaton shift will shift the k equals 1 case. So with a shift by 1, all the other stuff follow the same equation, and then you're going to write down something like 3/2 dd tau 1 equals so this term I write from dilaton shift. And again, this is a famous equation. This is called a dilaton equation.
So if you replace the isomorphism S1 by other group, this is just the function is just 1 over the top class.
Oh.
It's a top class.
I see.
1 over the top.
Oh, I see. That's a great point. I see. Ah, I see. That's a good point. I've never thought about it. Maybe you can do other group as well.
Yeah, well,
I
that's
see.
similar to
Yeah,
what
yeah,
we
yeah.
do in that field, right?
I see, I see. That's a great point. Thanks. Now, yeah, actually you can also do like L1, L2 essential. You can write down the corresponding classical Virasoro equations. But it can do some other stuff. So let me mention one more thing, which can basically end the story. And one more thing I wanna mention is the third equation, because this equation is going to be important for us later as well. So, oh no, it's here. So, great. Let me just write this one as a gradient equation. This will capture the degrees of this generating function. So this Lagrangian now let's consider the following degree operator. Let's call this one G. Which map to T to the K, map T to the K to 2K minus 2 T to the K. So that basically remembers like each degree of T by 2, and then this whole shift by 2. So it's the same thing as remembering basically. So in this space, and degree T is 2. Basically, just to remember this gradient. Okay, so you see, like, so because by the shifting, so it's like degree of this object in this vector space is 2k and then minus 2. And yeah, this is one of the places where you have to explore a little bit about the mysterious degree 2 shifting in this space. Again, the lemma. This is actually not hard to prove as well. I just checked directly. And because of this gradient operation, like this point is basically fixed. And you can show without dilatation shift, this Lagrangian literally is actually a tangent. The vector field is tangent to this Lagrangian without shifting. But this vector field is not Hamiltonian vector field. This basically this is about a gradient, and actually the symplectic form has a particular degree under this gradient. This will imply that the generating function has a particular degree. So if you write it down, you will find the following.
Sorry, how should I think about this gradient?
It's like that. So this gradient looks like, so you see like S equals, this is my S, right? So as a vector space, it's like that. But my degree assignment is the following. Like, as I mentioned, like the T object has degree 2. So whenever you write down without this shifting, every polynomial here or Lorentz series here, every element T to the K, if I assign degree of T to be 2, so the degree have to be 2K. Then with this shift by 2, the degree of this object in this vector space will be shifted by 2 as well. And that's how you write down this degree operation. So basically this one says like equivalently, I mean, you can show, it's the same thing as saying that this Lagrangian is preserved by the state action, which map T to the K, a point here to lambda 2K minus 2 T to the K. And you can show this explicitly, I mean. this point is fixed. And if you look at what's happening here, if you do a little bit calculation, you find it literally still lies in this Lagrangian. So this observation implies the following. Because the symplectic form actually has a non-trivial degree under this grading. So you will find like the generating function is homogeneous of degree 6. And here we assign if we assign these variables like tau k to be degree 2 minus 2k. This is the opposite of this one. And yeah, that's also one of the reasons. Like another way to say this is like symplectic pairing has degree 6 in this case. So 6 shifted symplectic pairing. And this is very easy to show. So combining this 3 equations, combining like string equation, dilaton equation, and this gradient equation, you can show easily like that the generating function look like the following. So if you calculate,
just a gradient, not an equation.
I mean this gradient, yeah. So this one has degree 6. Yeah. You can do other way. You can also do Virasoro, but it's equivalent in this case. So you will find like the Taylor series expansion, Taylor coefficient of this function is calculated by the following, like by this 3, and then at the classical level, tau k1, tau kn, calculate this Taylor series expansion. If you calculate this nth order Taylor series expansion, the coefficient is given by the following number, moduli space of m point on rational curves, the side-class intersection. And this is a precise value is given by m minus 3 choose k1, k2, and etc. This is uniquely determined by these 3 equations. So this basically calculates the generating function of this Lagrangian like precisely by this formula. And this is a place you started to see a connection with topological, like pure topological gravity. I mean, this is like
this is a computational result, right?
This computational result, yes. But actually has it's like a B-model perspective of pure gravity, saying this way here. It's purely geometric.
The grading and the shift are related, right? Because of the grading, because of shift. It must be.
You can rewrite this one in terms of your Virasoro equation. You can go to.
It must be central extensions. Center and point.
Maybe, yeah. That's right. Yeah. That's right. Yeah. And this central extension tells you also the degree of the symplectic form. Yes, exactly, yeah. Okay. Now we have calculated this generating function for the case when the Calabi-Yau is at a point. Now the general case is follows easily. So it's a little bit more subtle calculation when you have you play with like a superspace, but the answer is going to be the same. So let me just say this in words. And now I can erase this part. Now let me explain. Motivated by this, let me explain this classical BCOV action. How we discover this guy. And now consider the Calabi-Yau case. In general, and then I explained like we have a period, like a co-chain period map, with the same formula to this space. Let's call this Lagrangian Lx related to this x. And similarly, like I'm gonna write this Sx to be x plus direct sum x minus the standard splitting I mentioned, like non-negative order in T and positive order in T. And then I can write it as a cotangent of the base. And then you can write a same thing as a same object, like this guy is a Lagrangian is a formal Lagrangian manifold. And you can write this object, which is the image of this period map, as the graph of something. Let me call this one I naught x. It's related to this Calabi-Yau. So this I naught x is a function on the base manifold. So non-negative part. And if you want to be precise about the gradient, you have to shift everything by 2. Now, basically same calculation. So the only non-trivial part is the T geometry. So because the formula is the same. The formula is the same formula. And so let's denote this notation, like T to K1, tensor blah, 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 T to Kn. So let's denote this bracket 0 as basically the genus 0 intersection, like in pure gravity. So by definition, this one is this formula. Or if you want, you can just put this combinatorial number here. Just a notation.
So, but this you define that using the mu, right?
Yes.
Yeah. And that, well, for any more Catan in Hochschild for more.
Yeah, yes. Yes.
Number.
Yes. That's right. Yeah. So this is basically formal. Yeah. I mean, as far as you have this product structure and this, it works. And also this pairing. So it's hierarchical pairing, categorical hierarchical pairing, then it works. And we extend this one to by the way, there's a lot of things which deserve to write, and yeah. So if students have some interest, you're welcome to. As I mentioned, like all this kind of including category calculations, all this geometry. Like, yeah, this is like many things can explore actually. Yeah, and you also mentioned quite many interesting questions along the way. So you have a lot of students. Yeah. But anyway. So let me just say in words, like this is extends linearly. Again, you can replace this one by appropriate object to, let's say, a map. Let's call this one which is a map from symmetric tensors of this S plus to S plus to polyvector field actually. So basically, whenever you have some t's, you do this kind of intersection, and you think about this one as coefficient, and you multiply all this coefficient, and that's what this means. Then the theorem is the one of the starting point of this work. It's basically this generic function is precisely basically same formula, trace. And this one starts from cubic term. And then the calculation is completely the same as above. So basically, we use this one as a coefficient. The key calculation is done already, and the other part is just do some coefficient calculation. And we call this one classical BCOV action. Bracket 0 is
trace of that.
yeah. This is trace. Yeah.
Integrating on X, right?
Yeah, integrated on X. Yeah. You can also have trace on the categorical level as well. You have a parallel parent and the trace parent, things like that.
So this is not it's only category, that would be definition.
Yes, I need a cyclic structure. Yeah.
And the dimension of X will be negative.
Maybe. I don't know. That's gonna be fun. I've never thought about it. Yeah. Okay. So before we before we stop, let me just quickly mention this relation with the original BCOV proposal. This resolved some of the puzzle. So if we let us write, like if we write, for example, my polyvector in terms of t orders, like t mu naught plus mu 1 t plus mu 2 t squared plus blah blah blah. So yeah, actually have a tower of fields like this, and if you write down the corresponding action functional, so the leading term, like the term without any descendant, is when all of the k's are 0. So you can only choose n to be 3. And that's going to be 1 over 3 factorial trace cubic mu naught cubed modular all the higher terms in T. And this one is the original interaction in this BCOV's Kodawa-Spencer gravity. On Calabi threefold. So he wrote something like that. I mean, in this original model, the field is given by all these divergence-free like the polyvectors. So let's call this one mu naught. The special mu naught lies in the kernel del. Like divergence-free vector field. And then the corresponding action functional they wrote for this Kodawa-Spencer is like the action function look like this. 1/2 trace mu naught del bar over del mu naught plus 1 over 3 factorial trace mu naught cubed. So this is the original action. This looks a little bit unusual, like because when you apply d bar to this object, by the Dirichlet lemma, it's going to be del exact, and you invert by one choice, and then you calculate this pairing, and this is a cubic interaction. And if you do variation for this vector for this action functional, you discover the standard Mori-Cartan equation for deformation of complex structures. And but the field here is non-local, as mentioned. You can not multiply an object by some kind of a bound function to localize fields, and this causes a lot of trouble for doing quantization. And this object, as I mentioned, can be viewed as a homotopic replacement of this kernel del. So this is like a fixed point. This is a homotopic fixed point. And now the whole thing is going to be local. And yeah, so basically it's basically the complex replacing this kernel del by this complex. Yeah. And then the theory becomes local, and also encodes all of these gravitational descendants. That's the comparison with the original Cutoff phase of gravity. And once you turn on these gravitational descendants, then all these degrees things can be implemented for other dimensions. So that's why this action function works in general for any Calabi of any dimension, but I don't know for negative. Okay, so let's make a break.
Okay.